Welcome back to Cloud 42. I'm James. This is part 2 of my Toolpost grinder build series. In part 1, we looked at the design of the spindle and the parts we're going to use. If you haven't seen that, links down in the description. You might want to go check that out. Today, we're going to actually start making some chips. Let's take a look at the parts we're going to make. I think I want to start with the spindle housing. Spindle housing is about 5 inches long and 1.5 inches in diameter. And I'm going to start by turning this out of 12L14 from some 1 5/8 stock that I have. Now, I think the plan is going to be to turn the outside to diameter, bore the inside out, get rid of the majority of the material, and then bore for the bearings and for the minor diameter of the threads. So I'm going to have to flip this around anyway to bore both ends. I'll probably just drill the center out from both ends and just do half of it at a time, flipping it around as I go. So I've got a 12-inch piece here of 12L14, and I think basically what I'm going to do is leave enough material that I can make another, that I can get another spindle housing out of it if I need to, if something goes wrong. So I'll leave just over 5 inches. And then use the rest. Okay, let's go over to the saw and cut this off. This is just some coolant. You know, I've seen a lot of machining videos on YouTube, and they always skip this step. Nobody ever shows the bandsaw cuts. I don't really know why that is. Because this is just riveting. First thing I need to do here is turn the outside diameter of this to 1.5 inches. And this is a pretty good amount of stick out for a small lathe and a small chuck like this. So I think I'm going to do this with a center. Okay, I'm going to take a very gentle facing cut just to clean up the end of this. That much stick out, I don't want to do too much here. I'm not liking that shatter. Let me take this a little bit lighter this time. Again, once we get a center in this, it'll be a lot better. Okay, next step is going to be to drill and put in a center. Got my drill chuck here. This is a number 4 center drill. Locked in the tailstock here. I do not like that chatter, but the inside of the hole looks okay. So I'll go ahead and load up a center in there and see what we can do. This is a live center. Make sure my bore is clean. Make sure the taper's good. Seat that. Make sure the center's clean as well. Lock the tailstock down. Center in there nice and solid. Get some good pressure on it. Lock that down. And let's see how it looks. That looks good. Get a turning tool here. Now this end's already faced, so we want to turn about 5 inches of this. So let's do maybe, let's turn 5 1/8 of it. A little more. That should be fine. I'm going to do a couple of things here. I'm going to put a dial in here again so I can see where to stop. Not that it really matters that much for this. And then I'm also just going to make a mark. Just to be sure, let me check and make sure I'm on center here. That looks pretty good to me. Maybe just a tiny bit above. That's just about right on. Okay. And set up to reach everything? I am. Okay, for feed, I am currently set to 5 thousandths per revolution. Let's just start with that and see how that does. And I'll probably take here 20 thousandths off the outside to start with. Oh, I like that. Throwing the tips down, breaking them off. Okay, let me get a micrometer. So let's see where we are now. This end we're looking at 1.595. At this end we're almost exactly the same. It's turning almost exactly cylindrical. Let me start by taking Let's just go ahead and take 25 and see how that does. Okay, let's see where we are for diameter. Looks like we're about 558. Okay, so that's going to be pretty much on size, but that surface finish is impeachable. Looks like we've got about 1.5 thou left on there. Oh, that's interesting. About 1.5, 1. Okay, so. See if I can polish that up a little bit. It's about 1/2 thou. That's just very close to size. That's very close to size. That's right on size. So I just got about 1/2 thou right up at the very top of that. I'll go ahead and take just a little bit more then. That's getting pretty close. I'll grab some Scotch-Brite. Okay, that looks pretty good. I took a little break and let the part cool down, and so let's see where we got on size. That is dead on 1.5 inches. That's maybe 2/10 under. That's maybe 2/10 under. That's maybe 1/2 thou. That's about 6/10 under. So we're within a thou of being right on size. I'm not really happy with that surface finish, but the part's on size, so it's just gonna have to do for now. Now, while I've got it in here, I think I'm gonna try to hog out the majority of the material from the center of this. I don't wanna be here all day, so I wanna drill it. I do have a 57/64 drill for this lathe, but let's go to the computer and check and make sure I've got a good recipe for that. I don't wanna break anything, and this is a small lathe, and that is a really big bit. So let's see what kind of horsepower is actually required for that cut. This is G-Wizard. This is a software product from CNC Cookbook. I don't have any affiliation with them. I'm just a happy customer. I paid full price for this. I use it generally for calculating feeds and speeds for CNC milling operations, but I find it handy also for, since I use generally small machines in my shop, I find it useful for calculating horsepower requirements and trying to understand just what kind of cuts I can take on these machines. So I've got a profile in here for my Grizzly G0602 lathe, and I have a 57/64 taper shank drill that I want to use to drill out the spindle body. Let's do some calculations here and see if that is realistic. So for material, low carbon steel is fine. It's actually 12L14, but that's going to cut similar to 1020. And as a tool, I'm going to use a high-speed steel twist drill. I've also got options in here for high-performance coated drills and carbide. This is just ordinary high-speed steel. Tool diameter is 57/64, which is, whoops, that's not right, which is 890 thousandths. So let's put that in. Stick out is 6 inches. It doesn't really matter because it's not a side milling operation. Cutting depth 5 inches. Okay, so just as an initial solution, it is recommending 285 RPM with a feed rate that results in about 14 thousandths per revolution, 7 thousandths per tooth chip load. I guess it's the same as this 7.9 up here. Now, G-Wizard has a slider here so you can tell it how aggressive you want to be, and that's at 100% aggressive. If we pull it all the way back to conservative, then they're going to recommend a much slower feed of 3.5 thousandths per revolution. And then you can give you an idea of what the horsepower is. So that would be about 1.7 horsepower. And the full on aggressive, it's about 3/4 of a horsepower. Even though the machine has a nameplate rating of 1 horsepower, I don't feel comfortable running that at 3/4. I think that's unrealistic, especially since we're going to run it close to its slowest speed, which means we'll have the most belt reduction, which means we'll have the most torque on the final drive. And so I don't think that kind of horsepower number is realistic. But if we turn this back a little bit and say go much more conservative, this gets us down into a 1/3 of a horsepower kind of range, and that seems much more reasonable. We're at 257 RPM here. This lathe doesn't have that speed. It's not a variable speed. It goes straight from 150 to 300. So let's see what happens if we limit that to 150. If we go down to 150 and then start playing with this slider, we can get to kind of a 1/4 horsepower kind of requirement, going about 8 thousandths, 9 thousandths per revolution. So this is 4.5 thousandths chip load per tooth on the drill. And that seems pretty reasonable to me. So I think at 150 RPM, we could go as heavy as consuming 4/10 of a horsepower if we push it really hard, or if we go really easy, it's something like less than 10% of 1 horsepower. And that seems perfectly doable, and I can modulate that just by controlling how fast I push the drill. So this seems entirely reasonable for this machine. Let's go drill it. This is a brand new 57/64. Is that right? Yep, 57/64 drill. I want this to get this good and seated. Okay, I think that's good. Now let's lock down tailstock. Okay. Now this will be the largest drill I've ever run on this particular lathe, so Get some oil on this and see how she does. Ultimately, I want to go in 5 inches, a little bit more, so I can part off into the hole. So let me mark that on the drill. So I can tell when I'm there. Okay. Here we go. Sure the tailstock's tight. It is. Okay, that's the drilling operation done all the way through to the end, and that was a bear. That was a lot of work. The part's extremely hot. This little lathe is not really meant to do that. I got it done, and I've had enough. Next thing I need to do is just set this thing up to run true again, because it's warped or it's pushed slightly off center just because of the drilling. That's close enough. I'm just going to part this off now, and then we'll be ready for the next operation. I'll make sure I get my 5 inches here. I actually want to go a little bit more than 5 inches, so that I've got some room to face it off to length in the end. Okay. And let me change this angle so you can see a little bit better what's happening. Okay, let me put something in the tailstock here to catch that when it comes out. Okay, that drilling operation is done, but I can tell you that was way less fun than advertised for a variety of reasons. The drill actually went through fairly well. I'm pretty impressed with this drill. This is a YG1 drill, costs less than $10, and after pushing through, and you saw part of what was involved with getting this thing through that part, it looks really good. I can't see any wear on the edges. The edges are still very, very sharp like they were from the factory. The margins look really good. So I like these YG1 drills. I will buy these again. As for whether I will drill something this large on this lathe again, remains an open question. The lathe technically does have enough power, but there were a couple things that went wrong. One of them you saw as I was drilling that, it kept stopping, and the reason is the belts were slipping. Plenty of power, not enough torque through the belts in low gear. Yeah, I guess I should say low belt. Ultimately, I just tightened up the idler, and that took care of it. And so then after that, it wasn't stopping during the operation. The thing that got really difficult was the ram and the tailstock got really stiff to the point where I had to physically grab hold of this with both hands to get it to turn. And at first I thought the issue was just that it was taking so much force to drill. But in the end, it turned out the ram itself was getting stiffer. And I finished the job, and you may have seen me wearing gloves. That's because I had to wrench and hang on to this thing. I don't normally recommend wearing gloves when operating a machine. That story will probably have to wait for another time. If you want to tell me about how horrible it is that I wore gloves while operating a machine in a YouTube video and that I'm poisoning the minds of our youth, the comment section is down below. Go ahead and tell me down there. Let me show you exactly what was going on. You can see this is turning very, very freely now, but it got to the point where it took two hands wrenching on this even to retract the ram. Let me spin this all the way out. You can see it's moving very freely now. In fact, I can just pull this out. Pulling the ram out was impossible before. I had to work with the screw and a hammer and a punch, and I had to pound this thing out with a dead blow. If you look at the top of the ram here, there's a slot milled in it, and that slot is to take the screw in the top of the tailstock that keeps the ram from spinning. And what had happened is that under the really heavy torque of drilling, this edge was getting chowdered up. What was happening is the screw was bearing against the inside edge. I don't know if you can tell that it's not perfectly flat anymore, but the pressure, make sure I get this right, yeah, the pressure this direction against the slot was actually Brinelling the edge of this and forcing the metal to rise. So it was pressing in. This is apparently not that hard. And the screw in this import lathe didn't have any, it didn't have a plug on the end. It was actually just the threaded part of the screw, and it was actually impacting this edge of the slot and causing the metal here to rise 5-6 thousandths. And that was enough to jam this in the bore of the tailstock to the point where I had to hammer it out with a dead blow hammer and a punch. The edge here, ultimately I just came back through here with a couple of stones with an aluminum oxide slipstone and then a fine Arkansas stone to polish it off. I just took off that metal that had risen up along the edge there and then polished the whole thing up with Scotch-Brite. And now it goes very, very easily into the slot and fits. And let me get this lined up with the screw. There it goes. And locks down, but also spins freely, which is something that wasn't possible before. Let me show you what I did to the screw to try to keep this from happening again. The original screw was destroyed. Here's the new one that I made. And you can see that I turned a portion of the end of the screw cylindrical and removed the threads. And I don't know if you can see that or not, but it's slightly undercut in the hope that it won't bear on the very top edge of that slot, but will bear down inside the slot. Time will tell. This is just an alloy screw that I hard turned. And this seems to have solved the problem. And we will see long term if it stays solved or if I have to revisit this again. Okay, the next thing to do on this part is going to be to bore the center of this out to 1 inch. I want to bore it so that it's concentric and also to get the size on to 1 inch to make sure we have clearance for the spindle. And to do that, I'm going to want to dial this in, which means I'm going to want a 4-jaw chuck. So let's change the chuck out first. Okay. Now this has only been faced on one side, and then one side was cut off. This is the side, looks like it was parted. This is the side that's been faced. So we'll go in with that out. That's about as deep as it can go. I don't want to run it actually against the spindle nose, so I'll pull it back ever so slightly. You know, sometimes getting the square peg in a square hole is the hardest part of my day. Okay, it's in, it's not running true. Let's grab an indicator and dial that in. Okay. Sure we're going to clear here. And not concentric at all. Okay, we're within a thou. Let me go out here and look at the end, since this is where we're going to be ultimately boring the registers. And I need those to be as concentric as possible. Within a thousandth. But I can never leave well enough alone. Let me give it a shot, see if I get just a little bit closer. There we go, that's about half a thou. That is good enough. Okay, let's see how she spins under power. That looks pretty good. And that is 2400 RPM, which should be good for this because I'm under an inch in diameter. So at an inch in diameter, this lathe, 2400 RPM is the max. And at 1 inch in diameter, that's going to work out to a surface feet per minute somewhere between 600 and 700. And with carbide and mild steel like this, should be shooting for about 800, 850. So that should be good. Let me grab a boring bar here. And wouldn't you know it, I don't have one in a tool holder. I will soon. Now, I'm going to want to bore this. This is 5 inches, and I want to go the full depth all the way through it. But I'm not going to go through it from one side, which means I need to go about 2.5 inches from each side. So let me set this to, let's say, 1/8 of an inch over 2.5. So then when the tool bottoms out on the face of the part, I'll know I'm to depth. Let's touch off and take a light cut and see how we do. Caliper dimensions should be just fine here, and then as we get closer to 1 inch, I'll break out the telescoping gauges. So we're about 9/11. We need to take about 89 thousandths, 90 thousandths. So let's start. Let's take 20 off of each side, which will take 40 out of the bore. That puts us at about 941, so that was just about right. We'll take another 20. Should put us right about 981. Now let's see how close we got. That says I'm about 3/1000ths over. And that actually makes sense. So I would have cut a little bit oversized because that last cut was a had much less tool pressure because I was only taking 10/1000ths off of material off the surface instead of 20. Okay, now let's switch and let's bore the bearing race. And this is the one that's the critical diameter. And it looks like we need to go 433/1000ths deep. And the dimension is 1/260. 1 inch 260. Okay, so I'm going to shorten up this boring bar because there's no reason to have that much sticking out. And the total depth I actually need here is less than 1/2 inch, so I'll pull that back as far as I really can and still get the screws to clamp on it. Okay, so let's just go ahead. Let me set up a dial indicator here so we can actually see how deep we're going. Okay, let's take a cut. Okay, we're trying to head for 1/260 here. And I need to get the next micrometer. There's 1 inch and looks like 26. So I got 117 to go. So let's just take it 20 at a time. 20, this will be 40. 60. 80. 80. Now let's check and see where we actually are. Rough sanity check with the calipers. We're at 178. Check with the micrometer. Looks like about 180. I'm going to take 20 and then measure and then take the rest in, try to take the rest in 2 passes. That looks like 222. So we take 6 more to hit our dial in exactly. Let me double check here and see exactly what the size of the bearing is, because that's ultimately what we're trying to do, is fit this bearing. It looks like the bearing is 259, so 260 will give me 1 thou clearance for the bearing fit. And just as a sanity check, yeah, it doesn't fit yet. So I think we need to take 6 thousandths, and this should be the last pass, and we should be right there, and everything will be perfect, right? Well, let's see what we got. Well, that looks like 1/260. Let's try it in another spot. One 261 it looks like. $260.5. That looks pretty good. Let me take the burr off that edge. See if we can actually fit the bearing. Well, it's close. I think I'm going to take a spring pass. Yeah, that was a spring pass, but it looked like it was taking material, so let's see how bad it is. Okay, it fits, but it's definitely oversized. Should be okay though, since we're going to clamp it on that outside race anyway. Let's see what we actually hit. You know, we're oversized for this one now. $264. Well, that's not awesome, but we'll live with it. Okay, so the next one I need to bore is the counter bore that's going to ultimately be threaded for the cap. And that is 276 thousandths deep. So let's come back here, touch the surface and measure that. We're currently at 1/325, and we're trying to get to 341. Looks like 1.340. Let's see, that would be 350. 343. $342, and we're trying to hit 341, and the spec on that is 341 plus or minus 4,000, so we are there. Check one more time, just for kicks and giggles. That says 343. Okay, so hit the spec on that. Take off the sharp edge because nobody likes to get cut. See if I can. Okay. Okay, the bearing fits, turns freely, it's not rubbing on anything. So now I just have to flip this around. I have to do exactly the same thing on the other side. You don't want to watch that. I'll do that, and then I'll come back when that's done. And that's the boring of the other side complete. I just put in a chamfering bit here and cleaned up the edges. Let's go back to the bench and see where we are. That is the spindle housing, turned and bored with all the registers. Everything is done on this except for the threading. You can see there's a register on the inside to hold the bearing, and then there's an outer diameter that's going to be threaded for the bearing caps to retain the bearings. Turning the second side of this went beautifully. It didn't have any of the problems that I had on the first side. And I realized after the fact that what a smart guy would have done would have been to film the second one and then lie to you and tell you it was the first one, so you would think that I was smart and talented. As it turns out, I wasn't smart and talented enough to think of that soon enough. Well, we've got a spindle housing and we've got a spindle. Let's put it together and see how it fits. I've been dying to see this. I don't have the spacers, but I'll just go ahead and run that all the way up to the shoulder. Oh, and that is beautiful. Look at this. That is so smooth. It is silent. I don't hear anything. Okay, I'm excited for the rest of the project. Okay, the next part to turn is going to be the bearing caps that retain the bearings. I think I'm going to turn those before I thread the housing, just because it's much easier to measure outside threads. I have thread wires I can use for that, and then I can use the part to actually check the threads when I'm threading the body. And the other reason I want to do it in that order is because this lathe has change gears, and setting it up for threading is kind of a pain, so I'd rather just do it once. Thread these parts, and then after that's done, come back and thread the spindle to match. That will be the subject of part 3, and we'll start that process soon. Be sure to give me a thumbs up if you like what you're seeing, and subscribe to make sure you get notified for future videos. Thanks for watching.